Hey everyone, in this video we are going to solve this neat little problem that involves counting solutions to a complex valued equation. This is problem number 5 from the 2022 AIME Test II. So without further ado, let's go ahead and get on into it. So the problem says, let w equal square root of 3 plus I over 2 and z equal negative 1 plus I square root of 3 over 2. Here I is equal to the square root of negative 1. Find the number of ordered pairs, Rs, of positive integers not exceeding 100 that satisfy the equation I times w to the r equals z to the power of s. Okay, so first I would like to better understand what solutions to this equation will look like. And this equation involves a power of w and a power of z, where w and z are these complex numbers. Now, to take a power of a complex number, it's a lot easier if you have that complex number in polar form rather than standard form like this. So the first thing I'm going to do is convert these numbers to polar form. So I'm going to draw a little circle and put these on there. Okay, so I have a unit circle here. The nice thing is that both of these numbers I know do land on the unit circle. This is the square root of 3 over 2 plus I times 1/2. So that is going to be right about here on the unit circle, where this point is square root of 3 over 2, 1/2. And I know that this angle here is going to be pi over 6 just from the standard unit circle. So that means that w is going to equal to e to the I pi over 6. Next, z is equal to negative 1/2 plus I times the square root of 3 over 2. So that's going to be somewhere over here, where this point is negative 1/2 and square root of 3 over 2. Technically, I should have an I here, I suppose, and I should have an I in here as well, since we're in the complex plane. And again, just from the unit circle, I know that this angle from here to here, that is going to be 2 pi over 3. So that means that z is going to be equal to e to the I times 2 pi over 3. Great, so now that we have that, let's go ahead and just plug these expressions into our formula here so that we can get a better sense of what this is going to look like. So this is going to be I times w, which is e to the I pi over 6, to the power of r, and here r is just some integer between 1 and 100, and we want that to be equal to z, which is e to the I times 2 pi over 3, to the power of s, which again is another integer from 1 to 100. Now in the end, my goal is to count all of the r and s pairs that will work in this equation. So I'm just going to try to simplify this as much as I can. Maybe get r and s on the same side so that I can maybe get a better sense of what has to be true about r and s, so that maybe I can count how many of those r and s values there are. So I think I'm just going to combine everything that I can here. I'm going to take this I and turn that into polar form as well. We know that I is up here on our unit circle, and that is at an angle of pi over 2. So I is e to the I pi over 2. And in fact, I'm just going to go ahead and replace that right now. Now let's just combine these things together. And for clarity, so that I can write big enough, I'm going to use the notation where instead of e to the power, I'm going to write exp and then put the power inside here. So this will be e to the power of I times pi over 2 plus I times pi over 6 times r. And that should be equal to e to the power of I times 2 pi over 3 times s. And then multiplying both sides by e to the negative I 2 pi s over 3, I would get this. E to the power of I times pi over 2 plus I times pi over 6 times r minus I times 2 pi over 3 s. And that's going to be equal to just 1 on this side. Now finally, let's clean all of this up a bit. So if I make some common denominators here to add together, pi over 2 is the same thing as 3 pi over 6. So let's go ahead and do that. And then this one would turn into 4 pi over 6. Now we can go ahead and simplify this out. So we have e to the power of, I'm going to factor out an I times pi over 6. When I do that here, I'm just left with a 3. Here I factor out the I pi over 6, I'm just left with an r. And here I factor out the I pi over 6 and I'm left with a minus 4s. And that's all equal to 1. Now this is actually really nice because I know that this expression here is going to be equal to 1 whenever this piece in here is a multiple of 2 pi I, so some 2 pi I times n. And since I have this 6 in the denominator here, this whole thing will be a multiple of 2 pi I if this piece in here is a multiple of 12. So I want this to be some 12 times k, say. So I know that in order for Rs to be a solution to this equation, I'm going to need this 3 plus r minus 4s to be a multiple of 12. Okay, so we've reformulated our question to something that I think is a little bit easier to answer. And throughout the rest of this, I'm going to use this notation from modular arithmetic. I read this as 3 plus r minus 4s is congruent to 0 mod 12. That just means that if you take this and divide it by 12, you get a remainder of 0. So that means that this thing is a multiple of 12. Okay, so this expression though, 3 plus r minus 4s is congruent to 0 mod 12. By subtracting 3 on both sides, we can see that this is true whenever r minus 4s is congruent to negative 3 mod 12. And then by multiplying by negative 1 on both sides, we get that this is true whenever 4s minus r is congruent to 3 mod 12. And now I'm going to count the solutions to this. We're going to have to do this by breaking up into some cases. So we'll take a look at cases for 4s. So this is a multiple of 4 here, 4 times s. And if you take a look at the remainders of multiples of 4 mod 12, so the remainders of multiples of 4 when you divide them by 12, you would find that 4s has to be congruent to either 0 mod 12, so a remainder of 0 when you divide by 12, or 4s has to be congruent to 4 mod 12, so a remainder of 4, or it can be congruent to 8 mod 12. These are the only options. Let's take a look at what happens in each of these options. So let's go ahead and name these. We'll say case 1, case 2, and case 3. So let's take a look at each of these cases. So case 1, that's going to be when 4s is congruent to 0 mod 12. Now, if 4s is congruent to 0 mod 12, then this would become a 0, and you'd get negative r is congruent to 3 mod 12, or r is congruent to negative 3 mod 12. And also, because 4s is congruent to 0 mod 12, this happens whenever s is a multiple of 3. So whenever s is congruent to 0 mod 3. So what we can do now is count all of the pairs Rs between 1 and 100 that satisfy these relations. Before we do that, let's go ahead and write down similar relations for case 2 and case 3. So for case 2, we are going to have that 4s is congruent to 4 mod 12. Coming down here, if this piece is equal to 4, we subtract 4 on both sides to get negative r is congruent to negative 1 mod 12, or r is congruent to 1 mod 12. And then as far as s is concerned, 4s is congruent to 4 mod 12. That happens whenever s is congruent to 1 mod 3. So whenever s is 1 more than a multiple of 3. And then finally, let's take a look at case 3. Here, 4s is congruent to 8 mod 12, so I would replace the 4s with an 8. Subtracting 8 on both sides gives negative r is congruent to negative 5 mod 12, or r is congruent to 5 mod 12. And then again, as far as s is concerned, 4s is congruent to 8 mod 12, and that happens whenever s is congruent to 2 mod 3. Okay, so this is great. We've really reduced the problem down now. All I have to do is count the possible pairs that exist in this case, the possible pairs in this case, and the possible pairs in this case. Let's do that now. Okay, let's start with case 1. How many values of r between 1 and 100 are congruent to negative 3 mod 12? Well, I can figure this out pretty easily by just writing down some multiples of 12. So I just want to count the number of r values between 1 and 100 that are 3 less than a multiple of 12. Well, there's one 3 less than this number, there's one 3 less than this number, and so on all the way until I get to this one. The one that's 3 less than 108 is bigger than 100, so I don't want to count it. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8 of them. So there are 8 r values for this case. And how about s? Well, I need to count the number of multiples of 3 there are between 1 and 100, which is really easy if you write down the numbers between 1 and 100 in a certain way. Okay, so here are all the numbers from 1 to 100, and specifically in this column are the ones that are multiples of 3. And there are 33 rows here, 99 divided by 3. So that means there are 33 possible values for s, which means the total number of pairs is going to be 8 times 33. Let's rinse and repeat for the other cases. So for this one, we want to know how many numbers are congruent to 1 mod 12 between 1 and 100. So there's one that's here, 1 more than 0. There's one that's 1 more than 12, and so on, all the way until we get down to there's one that's 1 more than 96. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 of these R values. And then how many S values are there congruent to 1 mod 3? Well, that's everything in this column here. We already know that there were 33 rows here, and we add on one more for the 100. So that means that there's a total of 34 S values that are congruent to 1 mod 3 between 1 and 100. Okay, and then finally, the number of R values congruent to 5 mod 12. Well, there's one that's 5 more than 0, 5 more than 12, all the way down until you get to one that's 5 more than 84. However, if you add 5 to 96, that's bigger than 100, so I'm not going to add in that one. So just from here all the way down to here. So 1, 2, 3, 4, 5, 6, 7, 8 of them. And then how many numbers are congruent to 2 mod 3? Well, that's going to be this column here. And again, there's going to be 33 of those. And to get the total number of possible pairs, I'm going to add up all of these. And you can just plug this into a calculator, or you can get a little bit clever with how you add this so that you can do it in your head. So we've got 8 times 33 here, plus 8 times 33 over on the end, plus 9 times 34 is the same thing as 8 times 34 plus 34. So now I can go ahead and factor out the 8s from these first three. So I get 8 times 33 plus 33 plus 34. Plus this last 34 here. Well, this inside the parentheses is 100, so that's 8 times 100, which is 800, and then you add 34, so this gives you a total of 834 pairs RS, where R and S are between 1 and 100, and such that R and S are solutions to this equation.